This is for section 2.4 through 2.6, growth and decay models, derivatives of logarithmic and exponential functions of different bases. The first thing I want to point out is a formula that you will find very useful. The formula does vary depending on which textbook you use. And I know some of you like to Google around to look for different examples. So I just want to make sure you are aware that the formula is not always exactly the same, although technically, mathematically speaking, it is exactly the same. So this is the formula for growth and decay models, and I'm going to talk about this one here because this is the one that we use in our textbook. And the P of t represents the population at any time. And the population at any time, if it's growing or decaying, is really based on an initial amount. And then we have this letter here, which is technically a number. It's like pi. We know that pi is a Greek letter that represents approximately 3.14. Well, E is approximately 2.71828. And it is a natural growth rate or a natural decay rate. And it's all based on how much you start with, the amount of time that it's either growing or decreasing, and some underlying constant value. So this is the formula that is going to be probably the most important one for this section here. So you do need to try to commit that to memory and get a lot of practice in actually applying it. So let's look at problem number 1, example 1. Example number 1 says a bacteria culture starts with 500 bacteria. So this is going to be our initial amount. And after 3 hours, there are 8,000 bacteria. So if we started off with 500 bacteria and we have grown to 8,000 bacteria over a 3-hour span, this is going to be a growth problem because we have grown from 500 to 8,000 over a 3-hour period. If you refer back to the formula, this 500 is actually the initial value. So this is the P naught value. And of course, the time t here is 3. So this would be the time. And we know that after 3 hours, our population at time 3, excuse me, our population at time 3 is 8,000. So this would be our P of t. Okay. So part A says, find an expression for the number of bacteria after t hours. Well, the only thing they're really having us to do in part A is to determine whether or not we know how to fit everything into the formula. And we've already said that 500 is the initial value, so that goes into the P naught slot. E, of course, is built into the function. It is required part of the function. In fact, without E, none of this would even be possible. And we know that the time is 3. So that would be our expression, 500e to the power of kt. And then it says to find the number of bacteria after 4 hours. Well, once we establish the initial equation, we can actually use that initial equation in order to solve various problems. So if we want to figure out how much bacteria we have after 4 hours, we just plug that into the equation. Now you may be wondering, where did this come from? Where in the world did the 0.9242 come from? Well, if we scroll back up, we can see that a fundamental part of the problem is this underlying constant value, K. Sometimes they will give us the growth constant, but many times we will actually have to solve for the growth constant. So let's take a look and see how I came up with that. Again, we know that we have 8,000 bacteria when the time is 3. So this is our T value. And we know we started off with 500. And if these are growing at a constant rate, or actually at an exponential rate, I should say, then K is some value that is constant. And I have to solve for that. Well, the first thing I choose to do for simplicity is to go ahead and divide both sides by 100. And that will do away with the zeros on the right side, and it will take 2 zeros off of the left side. So that leaves me 80 is equal to 5 times e to the power of 3k. And then I divided by 5 on both sides, and that left me with e to the power of 3k on the right. And of course, that leaves me with 80 fifths on the left. Now, 80 fifths is 16, so I could call this 16, probably should have. That would have been a little easier, perhaps. And notice that on the right side, we have an e to the power of 3k. And we learned last time that if you want to do the inverse of e raised to some power, you have to introduce a natural log. So I chose to introduce ln on the left side, which means I have to introduce ln on the right side as well. And of course, if you introduce ln on the right side, these are inverse operations, which leaves me with 3k is equal to the natural log of 16. And then I just divided both sides by 3, and that leaves me with k being equal to the natural log of 16 divided by 3. Be very careful when you put this numerator into the calculator. Make sure that you use parentheses to let the calculator know that you're only interested in the natural log of 16. Don't do natural log of 16 divided by 3. That's a totally different number. But once you put this into the calculator correctly, you should get 0.9242 for K. And I was able to derive that from the fact that I had 8,000 bacteria after 3 hours, and I started with 500. Once I knew all of this information, the only unknown value was K. And I just used the properties of logarithms to come up with K. And again, K is 0.9242. Okay, so now that we see how we got that, hopefully it makes more sense when you look over and you see the 0.9242 N for K. Okay. Let's see. When will the population reach 30,000? If you want to know how long it takes for the population to reach 30,000, what do? Let's think about that. What does the formula actually say? The formula says that if you want to know, if you know the population at a given time, or the population, period, you plug that in on the left side, right, for P of T. The initial value is still 500. E is still the same number it's always been, 2.718. And we figured out that K is 0.9242. Why did I put 30,000 on the left side? Because the problem is asking how long will it take for the population to grow to 30,000? The only thing that's not known is exactly what they're asking for, the time that it takes to do that. So what do? Well, the time it takes to reach 30,000 is what I'm solving for. I started off with 500. E is a constant number. This is a constant number. All I have to do now is divide both sides by 500. That leaves me with 60 is equal to e to the power of 0.9242t. And again, since this is e raised to a power, I'm going to introduce its inverse operation, which is ln. I introduce that to both sides, and that leaves me the natural log of 60 is equal to 0.9242 times t. Now, in order to get t, I just divide both sides by 0.9242, and the natural log of 60 divided by that gives me approximately 4.43. Let's look at the last question. From the plot in D, what happens to the population as time increases? What I did here was I went ahead and typed in, I can't remember if I used Desmos or some other graphing tool to get this, but we can see that as time increases, as time gets larger and larger, the population gets larger and larger. So let's see. Let's think about that here. As time increases, right? Time is moving along. What's happening to the population? Well, the population, right, is going up. We can see it's increasing here. And we can go back now and look at some of the things that we actually solved for. For example, we figured out that in order to reach a population of 30,000, which is here, we figured out that in order to reach a population of 30,000, it takes about 4 hours and 26 minutes, which I guess would be about right here. This is a very rough sketch, but if you went straight across at 30,000 and straight down, this would be 4 hours and 26 minutes, about 4.5 hours. What else did we solve for? Well, if we go back to part A, or part B rather, part B says to find the number of bacteria after 4 hours. And after 4 hours, we got a little over 20,000. So let's take a look at that on the graph. So here's 4 hours. If we go straight up from 4 hours, and then we go across, we can see that we run into 20,000. So that takes care of our first problem. If you had chemistry, or maybe even physics in high school, or in college for that matter, you probably have some experience with half-lives, and I'll let you investigate half-lives on your own. I will give you sort of a layman's definition of half-life. The half-life of a substance is the amount of time that it takes for the substance to lose 50% of its initial amount. Suppose that the half-life of a certain substance is 20 days, and there are initially 10 grams of the substance. How much of the substance remains after 75 days? Okay, so let's think about this. We know that our formula for growth and decay fits this model here. And a big clue here is half-life. And we know that the half-life of a certain substance is 20 days. And we know that the initial amount is 10 grams. So here's what I decided to do to get started. The first thing I did was I wrote the equation. I went ahead and substituted 10 in here for P naught because 10 is the initial value. And of course, E is an irrational constant. It's built in. And they want to know how much of the substance remains after a time of 75 days. As before, we need to go back and take our clues to figure out what is this K value? What is this underlying constant value? Well, to do that, I took the fact that the half-life of the substance is 20 days. Okay, so let's see how we figured out K. If I start off with 2 units of this substance, I don't know what the substance is, they didn't tell us. But if I start off with 2 units and I go down to 1 unit, and I know that it takes 20 days for that to happen, I would plug in 20 here for time. Let me review that. If I start off with 2 units of the substance, and I know that it takes 20 days for it to lose half of its amount, then that means after 20 days, the 2 is reduced down to 1. If I divide both sides by 2, I have 1/2 is equal to e to the power of 20k. Of course, we have e raised to a power, so I'm going to take the inverse of e on both sides, which is ln. And of course, 1/2 is just 0.5. So I'm going to introduce an ln on both sides. And that will leave me 20k on the right side. That leaves me the natural log of 0.5 on the left side. Now, in order to solve for k, I just divide both sides by 20. So k is the natural log of 0.5 divided by 20, which is approximately negative 0.0347. Now that I have k figured out, I can plug that in, and I can tell you after 75 days with an initial amount of 10 grams, after 75 days, I am down to 0.7409 grams. Now, some of you may have heard of a process known as carbon dating. And carbon dating is where they, let's say they happen to be doing an excavation project in the Middle East, and let's say they find a mummy or they find a dinosaur bone. They do carbon dating to estimate how long that person or that dinosaur has been dead, because the longer you are dead, the more carbon is present in your body, or maybe you lose carbon. It's been a while since I've studied carbon dating, but the principle is the same. In other words, they use a growth or a decay model in order to estimate the amount of time that a dinosaur or person has been dead. So let's look at another problem. Suppose that radioactive ion X, this is going to be our substance, suppose it decays at a constant annual rate of 4%. So we know that it's losing 4% a year. What is the half-life of the substance when the initial amount is 100 grams? Okay, so this one is, it's the same concept, right? We know that we are losing 4%. It's decaying at a constant rate. And we know it's going to fit a decay model.
Yes, Lisa.
We know it's going to fit a decay model. So what do we know? Well, we know that the initial amount is 100 grams of ion X. And we know that it's decaying at a rate of 4%. Well, since this is a decay problem, it's losing 4%. This is going to be negative 0.04. Do not put 4 there, because 4% as a decimal is 0.04. And again, we have E as the base, which is our irrational constant. And they just want to know, what is the half-life? Well, the half-life would be the amount of time that it takes to go from the initial amount to half of its amount, which would be 50. And the rest of this is just really algebra. So I've got the initial amount here. I want to know how long it takes to get to 50 if I know the decay rate. In this problem, they give us the decay rate, K. I didn't have to solve for it. So how long will it take? Let's solve for T. To figure how long it takes for radioactive ion X to go from 100 grams down to 50 grams. Well, I decided to go ahead and divide both sides by 100, and 50 divided by 100 is 1/2. And that leaves me on the right side e to the power of negative 0.04t. And at this point, since I have an e raised to a power, I'm going to take the inverse of e, which is ln. So I'm going to take the ln on the left side. I'm going to take ln on the right side, which leaves me the natural log of 0.5 on the left and negative 0.04t on the right side. The next step is to divide both sides by negative 0.04, and that gives me 17.33. In other words, 17 years and 4 months. Now you may be wondering, how in the world did you get 4 months out of that? Well, the 17 here represents years, and this is a fraction of a year, and we know that a fraction of a year can be expressed in months. So I just multiplied 0.33 by 12, because 0.33 is 33%. In this case, we're looking for 33% of a year, which is 33% of 12, and that gives me pretty close to 4. So 17 years and 4 months is how long it would take for radioactive ion X to go from 100 grams down to 50. Suppose a material decays at a rate proportional to the quantity of the material, and there were 2,500 grams 10 years ago. If there are 2,400 grams now, what is the half-life? Okay, so let's see. We're going to go back to our original model because we know that this is a decay problem, because we started off with 2,500 grams, and 10 years later, we're down to 2,400 grams. So we're diminishing in the amount of substance that we have. Since this is, okay, not sure what my computer was up to there for a second. I hope we're still here. So let me rephrase that. We know that it takes 10 years to go from 2,500 down to 2,400, and I decided to go ahead and divide both sides by 100. That removes the zeros on both sides. And then I divided by 25. So that left me with 24 over 25 is equal to e to the power of 10k. I introduced a natural log on both sides, which leaves me 10k on the right side. And on the left side, I have the natural log of 24 over 25. To get k by itself, I divide both sides by 10. And I realize that k is approximately negative 0.0041. Now that I know k, I can use that in the formula. And since I'm looking for half-life, I want to know how long will it take to go from 2 units to 1. That would be the half-life, right? That's what we're solving for. And I want to know how long it takes to go from 2 units to 1. How long does it take to lose half of its amount? We take the natural log on both sides. That leaves me the natural log of 1/2 is equal to negative 0.0041t. Then if I divide both sides by that negative 0.0041, and I put this in the calculator, I realize that the half-life is 169 years. So it would take 169 years for this initial amount of 2,500 grams to reduce itself down to 1/2 of that value. Suppose a bacteria population grows at a rate proportional to the population. There were 200 bacteria 3 days ago and 1,000 bacteria a day ago. How many bacteria will there be tomorrow? Now for this one, I decided to go ahead and draw a little, I guess, a little diagram here to help me keep up with what was going on. So I decided to let today be Thursday. And that means tomorrow is Friday. And yesterday was Wednesday. The day before that would be Tuesday. And then, of course, 2 days prior to Wednesday is going to be Monday. Okay, so why did I do that? Well, it says, suppose a bacteria population grows at a rate proportional to the population. There were 200 bacteria 3 days ago. Well, if I let Thursday be today, if I start here at today, then I know that 3 days ago, 3 days ago, I had 200 bacteria. And I had 1,000 bacteria just 1 day ago. So 1 day ago, which would have been Wednesday, I have 1,000 bacteria. The question is, how many bacteria will there be tomorrow? How many bacteria will I have here? Well, if this is actually increasing at a rate proportional to the population, then I know that it fits our model here, right? This is just an exponential growth problem. And I have 200 here on Monday. 2 days later, I have 1,000. And of course, now I have 1,000 bacteria reproducing. So this is definitely not linear. I want to be able to predict with some degree of accuracy how many bacteria I will have on Friday. So let's go back to the shed and see if we can't work this out. I know that I had 1,000 bacteria after 2 days. 2 days after I took my initial measurement of 200, right? Because Monday, I had 200 bacteria, so that's going to be the P0 value. And I know that 2 days later, I was up to 1,000. And if we solve for K, I won't go through all the details now because we've done that several times, but if I go from here to K, you can follow the work. We end up figuring out that K is approximately 0.8047. Well, the question is, if we start off with 1,000 on Wednesday, if I start off with 1,000 on Wednesday, how many will I have 2 days later? So I just plug in 2 here. This is my K value that I solved for. Of course, E is built into the growth model. And if we put that into the calculator, we will see that we will have approximately 5,000 bacteria on Friday. Now, some of you may be asking, is there not another way we could have figured this out? The answer is yes. There are various ways to figure this out. To me, at the time, this seemed to be the simplest. Could you start with 200 as your initial value, and you would have to count 1, 2, 3, 4 days? You could do that, and you will get pretty much the same thing, very close to 5,000. You hire an aspiring actor and agreed to pay her $12 million for 3 years. That's 3 years from now. If she signs her contract today, how much of your money should you invest at 6.2% to make the payment as promised? Okay, so let's think about this and try to put it into context. You're hiring somebody who's an aspiring actor, and you tell her that if she signs a contract with you today, after 3 years, you will pay her $12 million. How much of your money should you invest at 6.2% to make the payment as promised? So you go to the bank and you tell the bank, hey, in 3 years, I need $12 million because I've promised to pay this actress $12 million after 3 years. The bank says, well, you can invest at 6.2%, and we will help you grow to that 12 million. So the question is, how much of your money do you need to put in now in order to have that 12 million ready in 3 years? So what are we solving for? Well, we're solving for the initial amount. What's the initial amount of money you need to put in so that after 3 years at 6.2%, your money will grow to 12 million. This is a growth problem because we want to grow from our initial deposit up to $12 million. So we're solving for the initial amount. Well, if you divide both sides by this number here, e raised to the power of 0.062 times 3, if you solve for P naught, then you will see that the initial amount you need to deposit is just under $10 million. So if you invest $9,963,283, if you invest that, when you come back in 3 years, it will have grown to 12 million. Okay. Now we're going to change gears and we're going to go down and look at some formulas. This class is not designed for math majors, so you have an advantage. I'm not going to prove these formulas. If we were math majors working on math degrees, we would probably have to prove these, but we're not, so we're not going to do that. What I'm going to ask you to do, though, is to commit to memory, or at least have them handy when you take your tests, the derivative formulas for a to the power of x and log base a of x. If you have an equation, or a function rather, that says y is equal to a to the power of x. Now a represents a number, a constant. It could be 5, it could be 2/3, and x is going to be the variable. The derivative of a to the x is a to the power of x times the natural log of a. That's what you need to know. The derivative of a to the power of x is a to the power of x times the natural log of a. If you have a function y is equal to log base a of x, the derivative is 1 over x times the natural log of a. If you're wondering how you might prove that, you would need to look at something called the change of base property, and then you could do the quotient rule in order to prove that, but we're not going to do it in this lecture. So let's apply these new formulas here. Here we have y is equal to 2 to the power of x, and that looks a lot like this. So of x is 2 to the power of x times the natural log of 2. This is the exact answer. Now, if you are asked to round in some way or other, you might have to type in natural log of 2 into the calculator, but for all intents and purposes, we are actually finished with that problem. Let's take a look at another one. Here we have y is equal to 1.4 to the power of x. So again, this is just an a to the power of x, and the derivative is a to the power of x times the natural log of a. What about this one? This one is a little different. Here we do not have a to the power of x. This is a to the power of 2x, which means our power is a function that's not x. That means we have to use the chain rule, which is no big deal at this point, I hope, because we've been using chain rule for a while. So the formula looks the same. In other words, the derivative of a to u, where u is just a function of x, it's going to be a to the u times the natural log of a, which is what we've been doing, but we have to do chain rule. So we just have to tack on by multiplying by the derivative of u. So let's look at an example. Let's go back to 3 to the power of 2x. The derivative of a to the power of u is a to the power of u times the natural log of a times the derivative of u. And the derivative of 2x is 2. Typically, we like to flush our numbers to the front. So I just chose to move the 2 to the front. So that gave me 2. I probably should have said 2 ln 3, although it really doesn't matter. To me, it looks better this way. 2 ln 3 multiplied by 3 to the power of 2x. To me, that looks a little better. That completes that problem there. So chain rule hasn't left us. In fact, chain rule is not going away. So don't forget chain rule. Chain rule means you usually have to turn the crank one more time to put the derivative of that function in the answer. Let's look at a couple of examples of the other property here. Remember that if you have y is equal to log base a of x, the derivative is 1 divided by x ln a. In this problem, I have y is equal to log base 8 of x, and it's going to be 1 divided by x times the natural log of a, right? Because we have to put the natural log of a here, and in this problem, a happens to be 8. Don't forget that if we do not write the base out, it's understood that log is base 10. So this is just base 10. So the derivative of log x in base 10 is 1 divided by x ln 10. And again, I'm just applying the formula here. Now for the final problem. Here I have log base 3 of u. This is not log base 3 of x. If this were log base 3 of x, it would be a lot simpler, right? It would just be 1 divided by x ln 3. But we have here as the domain, we have a function here that's not x alone. It's just not what we're used to. Since x squared plus 1 is a function that's not equal to x, we have to use the chain rule again. Now the first part of the formula looks just like the previous problems, right? The derivative is 1 divided by the domain, which is x squared plus 1, times the natural log of the base, which happens to be 3. But again, since this is a function that's not equal to x, we have to multiply by the derivative of x squared plus 1. And the derivative of x squared plus 1 is 2x. And the rest of this is just simplifying. I multiplied the 2x times 1. That gave me 2x in the numerator, and of course the denominator is x squared plus 1 multiplied by the natural log of 3. And just as a closing question here, what about something like this? What about this one? What if you had this type of problem here? Well, we have x to the power of 3. This is old school here, not too bad. And then we have log base 5 of x here. And the question is, how would we find the derivative of this function? Well, since this is a product, we would have to use the product rule, right? We would have to multiply the first times the derivative of the second plus the second times the derivative of the first. That's just one of our old properties, right? That's the product rule. But now we have to apply the product rule within the context of our new knowledge, right? And that's how to find the derivative of logs. When I multiply x cubed times the derivative of log base 5 of x, this is what I get, right? Because log base 5 of x is going to be 1 divided by x times natural log of 5. But product rule says I must then add to that the second function times the derivative of the first. Well, the derivative of the derivative of x cubed is 3x squared. And the rest of it is just simplifying. This x down here in the denominator would take one of the x's out of the numerator. That goes from x cubed to x squared. That leaves me with x squared over the natural log of 5. And then over here, I just chose to take 3x squared to the front. And this is our solution. So even though we've moved on to the derivatives of logs, that does not mean that we can abandon things such as the product rule or the quotient rule and the power rule, right? We still have to use those things in order to figure out fairly complex derivatives. Thank you.